Hey class, so today we're going to be talking about waves and the properties of waves, but specifically we're going to start with mechanical waves. Okay, so let's take a look at this website about mechanical waves. Here's just an example to start with. So we have a droplet of water that is entering the surface of the water right here. Okay, so this is a point source and we have energy. Okay, and then the energy is being emitted into this body of water that is causing the ripples in the water, which are called concentric circles, so they're spreading out, okay? So this is an example of a mechanical wave. So sometimes the wave will be referred to as a disturbance, which is just the particle traveling, and then the medium is the space in which a wave travels through. So like in the example we just talked about, the medium would be the water. So the energy is traveling through that water. And here's an example of a guitar string. So we have a particle, the energy traveling through, and the string is the medium, okay? And something to note about this is that it has no displacement, so it is not actually moving. The medium is not moving. The particle is traveling in it, but the medium is not physically changing its position, okay? Okay, so here's just an example to think about. So there we have a batter. He's going to hit the ball. And a quick question for you. What do you typically, notice first? Do you hear the sound of the bat hitting the ball, or do you see the ball being hit? Okay, so we would typically see the ball being hit first, right? Rather than hearing it. So this tells us that light waves travel faster than sound waves. So if we just explore some more examples of a mechanical wave, which are particles traveling through mediums, we have a violin string, which was similar to the guitar string. So that particle is traveling through the string, and the string being the medium. We have the water waves right here. The energy is traveling through the waves, so the waves are the mediums. Well, the water is the medium, sorry. And then the phones, I don't know if you did this when you were younger, but phones that can be made from the cans right here in the string, we have the sound waves traveling through the string, so the string is our medium. And then just something to note, like we talked about earlier, light waves travel faster than sound waves. Okay, so these are two different types of mechanical waves, transverse and longitudinal waves. So a transverse wave is when the medium is traveling perpendicular to the particle. So the particle is always traveling, in this direction. And then the medium is going to, in this example, it's moving up, and the particle is to the right. So we have a perpendicular relationship that is formed, and same over here. So that is our transverse wave. An example of that is a crowd making the wave. Okay, so we have the energy being transferred in one direction, and the people are moving perpendicular to that. Another example is ripples in the water. That's a transverse wave. Excuse me. Okay, so then if we talk about longitudinal waves, this is when the particle and the medium are traveling parallel to each other. So if the motion of the wave is this direction, then the spring will also be moving parallel to it. It can be in this direction or in this direction, but it's still parallel, okay? So an example of a longitudinal wave is a sound wave. Okay, now we're just going to look at like what a transverse wave really looks like and what a longitudinal wave looks like. So first we're going to start with the longitudinal wave. So we see them moving parallel. And this is a transverse. See how it's perpendicular to the direction of the particle. There we go. Transverse. Okay, so the actual structure of the wave is pretty similar to the sine graphs that you've seen, or the cosine graphs if you've taken a trigonometry class. And so we're just going to talk about the structure. So we see that the wave starts here, and we're traveling along, and then we come right back to this vertical spot. Okay, so we call this a crest with a maximum. So this is the crest right here, and then we keep traveling along, and we get a minimum. And this is our trough, and then we end right where we started. So that is one wavelength right there. And then if we go along, we see we get another one. So we have a total of 2 wavelengths. Okay. So these terms that we're going to go over also relate to electromagnetic waves and light waves and sound waves, okay? So the displacement is the distance from equilibrium. So equilibrium is right at 0, right? And the displacement is the vertical distance. So if we go up this far, that's a displacement of maybe, let's call this 1. And then the amplitude is the maximum value of the displacement. So we want to look for the maximum, which would be, let's call this, we had 4, okay? So this is going to be 4, and then this would be -4. But we can also call this a maximum, but take the absolute value, right? We do not want a negative value, okay? This is going to be a positive value. Okay, then we have the wavelength, and the wavelength is the distance in which the wave reports itself and is denoted by lambda. So we're going to call this symbol lambda, and that's the wavelength right here. So we talk about a start. We start here, we have our trough, and then this section and this section create our crest. So we stop where we started, right? And yeah, so then here's our amplitude, our maximum. Okay, and then we'll proceed. Frequency is the number of waves passing in a single second. So if we have the same distance from here to here, we see that this has a much higher frequency because there's more wavelengths that are occurring in that distance than compared to here, okay? Let's flip back to here. We also have the period. Sorry, I just skipped right over this one. The period is the time it takes for one complete wave to pass a particular form. Okay, so we have our wavelength, which is very similar to our period. It's just that now our period is measured in seconds and not distance. So wavelength is distance and period is seconds. So how long is your wavelength? Is it a second, half a second, and then the wavelength is, well, the period is how long does it take. The wavelength is how long is your wavelength. Okay? So we're going to explore some problems with that later. By problems, I mean examples. Okay, so let's check this out. How are frequency and the period related? Because there are connections between these terms. If I can find it. Okay, if you just want to pull up your simulation, that would definitely be beneficial, but we can just go over it together. So we'd go on FET, and then wave on a string, and then here we go. So we're going to be exploring how frequency and the period are related, okay? Got this pulled up, and we're exploring the frequency and the period. And I'm going to use oscillate because that seems to be the most beneficial for this one. So let's go in slow motion because we've kind of got a lot to see when it's going fast. Okay, so let's do a higher frequency. So, whoops, high frequency. Okay, so here's our high frequency. So we've got about 1, 2, 3. It looks to me like we've got about 3 different areas of crests and troughs. So if we lower the frequency, what do we notice? Might take a while. So now we notice that we're only getting about 1 crest and 1 trough. So this tells us, I guess this is more so related to our wavelength, right? So this tells us, yeah, let's look at this one. This tells us that as we increase our frequency, what happens to our wavelength? Our wavelength decreases, which is also then related to our period, because that means we have the period is a shorter amount of time, right? So we note that the frequency and the wavelength and the frequency and the period are inversely related. And this is our formula relating frequency and period. So as frequency increases, the period decreases, and vice versa. As the frequency decreases, the period increases. Okay, so let's think about this question. What would be the frequency of a wave if the period is 0.25 seconds? And you've got a list of answers here. I'll give you about 30 seconds to answer that. Okay, so we need our formula. Frequency is equal to 1 over our period. And our period is 0.25, so 1 divided by 0.25. Whoop. 1 divided by 0.25 would be what? D, right? 4. So the frequency would be 4. So within 1 second, we would see 4 wavelengths. So we noted that we found that relationship. Okay, now we're going to look at what happens when we have one fixed end and a loose end. Okay, so let's flip over to manual. And let's look at the fixed end, and I want you to note what happens as it reflects and hits right here, okay? Slow motion. Ooh, I'll do that again. One more time. So we should notice that it reflected upside down, so it was inverted. It's upside down, so when you send a crest, you get a trough back, okay? And then what happens when one end is loose? Let's see here. Take a prediction at what you think will happen while I get this set up. Oh, we see that it comes back, right? But it is not inverted. It comes back the same way that it initially came off. So we see it making, yep, it made another crest. So you send a crest and you get a crest back. Okay. So now let's explain